Okay, today we're starting kind of into the real meat of statistics. Everything else was kind of introductory, and this is going to kind of get us to inference. And statistical inference is the thing that really kind of takes us from all the things that you might learn in other classes to where you start. You don't learn this until you actually take a dedicated statistics class. You've never really been introduced to this. And the idea is going to be, okay, we took a sample, but we know our sample isn't our population, correct? How accurately, how accurate of an estimate is it for our population? Does that make sense? And so we're going to talk about some things that you wouldn't actually do because we know we have one. Ours is one of these theoretical things. So, like, would you ever take a sample 1,000 times? No. Why would you do that? Just take a larger sample size. Um, but this theoretical idea of take a sample 1,000 times is going, well, I know my sample is effectively like it's one of I took a sample 1,000 times. That kind of makes sense. And so we talked about doing some simulations before. Simulations essentially show us, okay, I have this sample. It would fall, somewhere in usually a normal distribution of possible samples. And we'll talk about how to make that into a normal distribution. I think that's actually Monday, though. So, is my battery stupid low that it won't stay on? Yeah, that's the problem. So, really important terminology. I think we talked about this a little bit before, but mu, population mean, or population parameter, sometimes just called parameter. Okay. We're also going to introduce this as P, is also a population parameter. P stands for proportion. So if I say 70% of my population likes candy, that would be a proportion, not a mean. The mean would be 700 of my 1,000 in my sample. Now I could do 700 of 1,000 and get 0.7. Sample X bar is for my sample, and we've talked about that before, right? Sample statistic. Okay, there I can spell it. Again, a mean. The proportion one is p hat. Sigma is population standard deviation. Um, S is sample standard deviation. And those are going to be important distinctions to be able to make. There isn't a separate one. We use sigma and S, whether it's proportions or means. Okay. Does that make sense? You guys memorize that stuff? Like you just need to get it memorized because we're going to be using these variables and you have to know what they mean. So, sampling distributions. So, the mean income of a sample of household contacted by the current population survey was X bar equals 57,045. That is a statistic. Why is it a statistic? Why is it not a parameter? Okay. It uses X bar because it's a statistic, but that is a good giveaway. But the reason is really because it was a sample. You're using the sample statistic to try to draw conclusions about the parameter. This was from 106 million. You're drawing, well, I don't know how big this survey was, but you're trying to draw conclusions about the 106 million US households. If you knew what the mean was of the 106 million households, why would you bother taking a sample? We already know the answer. We don't need to draw conclusions about it. But realistically, remember we've talked about census and all those issues with not actually getting a full count with census. Even with census, which is hard to do, and I'm sure the US government spends billions of dollars on it every 10 years. I'm sure it's in the billions. And there's good reasons that they're trying to get it as absolutely accurate as possible, but it still misses stuff, right? So if you are a private company, you probably can't afford the census. It's not worth it. You can get good enough results by sampling a relatively large sample size. So, do you believe in ghosts? The Gallup poll asked a random sample of 515 US adults whether they believe in ghosts. Of the respondents, 160 said yes. So the population proportion is 160 out of 515, or 31%. 160 is not a meaningful number if you don't know how many were in the survey, is it? With that income, I didn't need to know how many were in the survey for that to be meaningful, did I? How accurately it's meaningful matters for the sample size. But oh, the average household's $57,000. That's probably from the late 90s, so hopefully it's a lot more than that now because things cost a lot more. But nonetheless, the idea here, this 160 doesn't mean anything without the sample size, so we probably want it to be proportion. The income, the sample size doesn't really change it. That's more of a mean type of value. Does that make sense? So we know that if you take a different sample, you will probably get different results. Sometimes you might get exactly the same. That happens. But a lot of times you'll get results that are different, sometimes slightly different, sometimes a lot more different than you'd expect. And a way to test how different they would be with simulations, where we go, okay, we think it's this amount. Let's simulate an experiment with that random amount. Okay, so baggage check. This is at the Guadalajara airport. Do you guys know where Guadalajara is? Did you learn that in Spanish class? It's somewhere, it's in Mexico. I think I've looked at a map. I think it's somewhere near Tijuana. So, customs officials, instead of stopping everybody, you get a light. You get a green light or a red light. I'm not sure that they still would do this, but if you get a green light, you just get to pass through. If you get a red light, you get checked. 70% are supposed to get green lights. So we can simulate this and see. They did a simulation. Says 0 through 6 was green. 7 through 9 was red. They took the first 100 entries and got p hat of 71. The second one, they got 62. For sample size 100, this is our distribution. They repeated this simulation 1,000 times. So if you actually did an experiment, it's pretty likely you're going to get somewhere between this. I think that's 56 and 83. Most likely, it's going to center around 70. If your distribution is unbiased, which if we're doing it with random, it better be unbiased. But if it's unbiased, the mean of the sampling distribution, so essentially the mean of all these proportions, or sometimes it'll be the mean of all the means, which gets a little confusing, but you're averaging all your sample means. The mean of the means equals the population parameter. Or essentially the mean of all the X bars from this distribution of possible samples equals the true mu. That's the definition of unbiased. A little interesting definition.
It's not the mean of means is equal to.
It is equal to mu
If it's unbiased.
if it's unbiased.
So if it is biased,
that mean of the means is not equal to the true mu. Now, again, you generally don't know what the true mu is, and you're not doing 1,000 means, so you have to look, is there something else in my sampling that would cause a bias? Just like we thought about when we did sampling design back in chapter 5. That makes sense? That there is it's really key that this is going to be there. But again, you don't know what that is. You don't know what it actually is. You might have some guesses. And what we're going to get into with statistical inference, well, the rest of the course, is going, okay, I have an X bar or a sample proportion. I know it's somewhere in my sampling distribution, but I don't know where. What conclusions can I draw? Okay, say I got a 64. Hopefully, if my statistics are performed correctly, 70% is going to be within what I would conclude. But it also means I could be concluding that it's probably between, 71 and 52 or something like that. So I get these intervals or different tests that go, well, I can conclude it to this level of accuracy. And I can only conclude it to that level of accuracy. If I want to improve my level of accuracy, what do you think I should do? Correct. Absolutely increase the sample size. We will come back to, I think it's this one that we come back to, and they do, instead of sample size 100, they do sample size 1,000. But here they're going to show it with random digits. If you select a random digit, each one is equally likely, correct? If you average two randomly selected digits, it is possible to get 0, 0. It's possible to get 9. You can get 9, 9. But they're going to average, the most common one is 4.5. And if you take all the possible averages, all 100 of them, and put them into this distribution, you get this triangular shaped distribution. For sample size 2, if you do this for sample size 10, what do you think it's going to start looking more and more like?
Flat.
Less and less flat. So 2 got less flat. It was perfectly flat with 1, like this. When we got 2, it started to get more triangular. If I go to 3, 4, 5, 6, what is it going to start going towards, do you think? It's probably actually flat around the edges, but what did I make a bad sketch of? No, no, no. Standard normal.
Yeah.
It's like the one in the back, the T is similar, but it looks the same. It really does. We'll get to that in chapter 11. And once T gets over, once you have sample sizes over like 10 and stuff, it starts to get really close. So, designing a sampling distribution. Are you a fan of the show Survivor? No? Well, that's okay. You didn't grow up in the early 2000s when Survivor was the big rage. Um, you actually weren't even alive. The Survivor started going out of style before you were born. So it was the big rage. Season 2 happened in 2001, and the estimate was 37% of adults in America watched Survivor. So the overall shape of the distribution should be symmetric and approximately normal, with a center close to 0.37. So they do a simulation of 1,000 of these things. And yes, it's centered at 0.37. These each have a width of, I believe it's a width of 3. So 35.5 to 38.5 is my center block. Does it look perfectly normal, perfectly symmetric? It never will. But that's pretty darn close. If we took this to 1,000,000, it would look more symmetric. If we did 1,000,000 samples of this. But notice the variability from 22 to, they've got the actual data, so from 22 to 54% for something centered at 37. That's a pretty good amount of variability. This is sample size 100. And we're going to use the variable n to represent sample size. Okay. Sample size is 100. Well, what do you think would happen if we went to sample size 1,000?
Get closer to it.
It's going to get narrower. Good. You're making the right conclusions. So if we show it with the same scale, it looks really kind of ridiculous, doesn't it? So they changed the scale so each one of these is one proportion, which a little weird in this look, but 0.38 is actually higher than 0.37. There's still some random variability. even within, um, and you should expect that. Is this still approximately normal with center at 0.37? Yes. I mean, yeah, sure, 0.38 is slightly higher than this 0.36, but it's not a ton. And 0.35 is higher than 0.39. I can't actually tell on 0.34 and 0.40. But this is approximately normal with a whole lot less spread. That makes sense? Here, let's make it, there's a better. And remember, our density curves are drawn over things to approximate them. A density curve is an idealized perfect situation. And again, if I did this a million times, it would get closer. So it's the amount of the more samples you do, the closer it's going to get to that perfect curve. Probably. Most of the time. There's probability. There's always that one weird time where, hey, those last 10 samples that we added were really off. It does happen, but the thing about statistics is there is no certainty. You are never certain with statistics. You are only certain to a certain percentage. And some of that times the percentage might be, I'm certain it's within this amount 99.5% of the time. You're like, oh, yeah, that's good enough, isn't it? Some of them it might be, I'm certain of it 90% of the time. If it's only 60% of the time, it's probably not good enough for anybody. Occasionally, 80% might be good enough, but usually not. It'll depend what it is, and as we go through inference, we'll talk about that more. So, unbiased essentially means the center is where it's supposed to be. And that's basically your definition of unbiased. So outside of unbiased, we can talk about variability. What do you think variability is? How spread out it is? You're like, oh yeah, it is morning. And some of the reason we want to make sure that these are very, loose definitions. The technical definition of statistic used to estimate a parameter is unbiased if the mean of the sampling distribution is equal to the true value of the parameter being estimated. Kind of what I said before, where the mean of the means is equal to the parameter. Variability is then going to have to do with our measures of spread. What are your two measures of spread? We've talked about this semester-ish, last couple months. I've had one of them up here already today. Standard deviation is one that goes with mean, right? What one goes with median? This has been a while. This was chapter 1. Yeah. I'll give you the letters.
Hundred.
Interquartile range.
Oh.
Q3 minus Q1. Yeah, I know. We cram a lot in these college classes kind of quickly. So, do you guys remember the 68, 95, 99.7 rule? Hey, there we go. What is this rule essentially?
Oh. In the normal.
So it applies to normal only, right?
That.
Yeah, yeah, this. What's within 68%?
That.
The middle 68, and how far away is that? X, that's one standard deviation. What's 95? And my below one should be a minus. X bar minus 2s here, X bar plus 2s, and three standard deviations was 99.7. And again, there's no amount that's 100. There's no set distance that's 100%. I mean, practically is something ever 20 standard deviations away? Not likely. Does it occur? Maybe if we did like uh, household income for Americans. There's probably somebody out there that's making 30, 40 billion a year that might be 20 standard deviations away. Hence why we usually use median for that. Because there's a lot of those outliers on the top end, and you don't have, zero isn't that big of an outlier on the low end. You can't have, and you can't, even if you're taking tons of debt, you don't have a negative household income. Okay, but back to our survivor thing. So we've got 0.37 plus or minus 2 times 0.05. So 95%, we had a standard deviation of, this is for my sample size 100, of 0.05. So to get the middle 95%, we do 0.37 plus 2 times 0.05, or the middle 95% falls within the interval 0.27 to 0.47. Is this the same interval according to statistics? That goes back to Tuesday. What do you guys think? It's Thursday. I'm gonna see if you guys can make this connection. The answer is yes. So this goes back to random variables. What's the in a continuous random variable, which a distribution is, what's the probability of any value? 0. But only probabilities exist within ranges. because there's so many infinite possibilities within continuous that the probability of any particular value among all the possible values, and if I say 0.37, I'm talking 0.37 to infinite decimal places, not 0.37000001. That's would be within this interval, or 0.27000001 is in the interval. 0.27 exactly is not, so these are the same. Usually in stats, they write them with parentheses, or at least in this book, as if it's not inclusive, but it doesn't matter. Like, you do need to know that if it comes out at 0.27, you include that because your thing functionally 0.27 is something rounded to 0.27, but you don't round up to that. That makes sense? And ultimately, we're going to be using this to conclude about an unknown population mean or proportion. So we're not going to know if it's 0.27000001 or not. Okay, we already talked about variability. So taking a look at this. High bias, low variability. Why is this high bias? Not in the center. It's a very tight grouping, but you missed the center. Versus this one, high variability, but it is centered around the middle, so low bias. High bias and high variability, definitely don't want that. This one, ideal, is low bias, low variability. Often very hard to get that D. I guess so. Which one of these? So there's one of each of the four. High bias, high variability, low bias, low variability, high bias, low variability, etc. What's A? That's probably high, medium high. I mean, it's kind of chunked in the middle here, but you still have this over here. But the center is not in the right spot. What about this one? That's the ideal low bias, low variability, high variability, high bias, or low bias, but high bias, low variability. Can I say the right words to go with what I'm thinking? That makes sense? So that is our sampling distributions. It's going to be Monday, we're going to talk about proportions and means. Okay. And how those two fit together. You guys will test on this stuff Wednesday, Thursday next week, chapters 7 through 9. You need to have it in on Thursday before spring break. And then, yeah. Yes, I agree. And then we will be coming back from spring break and hitting the what's the word I'm looking for? Um, inference, which is where I go, okay, I've got this sample. What can I infer about the population? That makes sense? Okay, now go ahead.